control of the segway. We consider the segway, which is this vehicle, which is normally unstable, but there is a controller to make it stable. So what we will do in this exercise, we'll try to compute the regulator so that it becomes stable, and then we can make the segway totally autonomous. So we ask it to go in a given direction, and the segway will go to this direction in a stable way. So by stable we mean that the body is at the top. So in this system we have 2 degrees of freedom. First, for the planar version, we'll consider first. So there is an instability with respect to the pitch, and the pitch, due to the fact that we have 2 wheels in this way, so the instability is only a planar stability, so that we will consider a 2-dimensional version of the segway represented on the right picture, and we'll try to find a controller for this. We need to find a model, which is recall here, and x1, x2, x3 correspond to the state, and this system is totally nonlinear. So x1 corresponds to s, the angle of the wheel, and x2 corresponds to the pitch, so theta. Now we assume that the only measurement we have corresponds to x1, I mean to the angle s. So there is a direct correspondence between s, this angle, and the position of the segway on the planar line. So there is some coefficient here, mu1, mu2, and so on, and they are related to the mass, the radius rho of the wheel. So capital M corresponds to the mass of the wheel, small m to the body, rho to the radius of the wheel, Jm and Jp correspond to the angular momentums, L to the distance between the radius of the wheel and the center of gravity of the body. So we have some coefficients like this. So we know that all these coefficients are positive. Now we have some values for the coefficients that will be needed for the simulation. So we'll apply a linear controller, and for this we'll have first to find the operating points so that we can linearize around these operating points. We will check that it is the system is controllable, and we will get some provide some simulation before computing the controller. So the system is represented here, and recall that we will first consider the planar version here. The planar version is this system where you have the only input u corresponding to the torque here that we can apply with a motor between the wheel and the body. The only thing we can measure corresponds to s. So it means that we'll need an observer to estimate theta. So we'll provide in this exercise a regulator. The regulator will have, so I recall that x, the state corresponds to s theta s dot theta dot. S corresponds to this angle, but more or less with a sign minus s here, the distance between 0 and the center of the wheel. The controller will have the form a state which correspond to x hat, which correspond to an estimation of the state x of the real system, and it will have the form IR, and the input will be y here. W is a wanted position. For instance, I want the wheel to be here. It corresponds to the set point. So plus PR multiplied by the input U, W, the input, and Y. And here the output of the system is U equal CR, so R like a regulator, that's why here or X hat, plus DR multiplied by WY. So this corresponds to the state equation of the regulator, and for this I have a method to compute this. It corresponds to the linear method called KLH controller. Okay, so the first question is to find the set points so that I can linearize. So for this I need some state equation, and the state equations that are given in this exercise are the following. Okay, so now for the first question, to find set points, I need to solve a system which corresponds to so a set point so that I can linearize. I start from this equation, the state equation of my system, and to have a set point I need to be able to stop the evolution, so to have this equals 0. So a set point x bar u bar satisfies the equation f of x bar u bar equal to 0. So it means that I have to solve this equal to 0. I remove this. So here it means that I have bar everywhere. So first, due to this, I know that x3 bar is equal to 0. So I have x3 bar equal to 0. I have also x4 bar equal to 0. So I have some simplification. This is equal to 0. This is equal to 0. And from this, I am able to rewrite this equation into the form. So I will write it, I can see some linearities with respect to the sign of x2. And with respect to u bar also, which is given here. And I will rewrite this in a linear form. So I rewrite like this, minus mu j mu 3 cos x2 bar mu 1 mu g j, so for the first column, and then here I will have sine of x2 bar u bar, and this should be equal to 0, the 0 we have here. Okay, so here I will have mu 2 plus mu 3 cos x2 bar, and here minus mu 1 minus mu 3 cos x2 bar. So to solve this, I will first check that this matrix is invertible. So if it is invertible, then I will know that this should be equal to 0. So how can I check that this matrix is invertible? I will compute the determinant of this matrix M. The determinant of M, so it is an expression which depends of mu1, mu2, and so on, and they depend on the mass, moment of inertia, and so on. And I can compute, easily check that this determinant is never equal to 0. So I will not do it here. So it means that this should be equal to 0. As a consequence, the operating points are satisfy x bar, u bar. So u bar should be equal to 0. And for x bar, it will have the form. So I need to have this equal to 0, but x1 bar can be what I want. So I will write it like this. This one require that x2 bar is equal to k pi, where k is an integer, and I know from this that the two others should be equal to 0. So what it means? It means that the segway can be, if here is 0, to be at equilibrium. So it is the set point correspond, the operating point correspond to an equilibrium due to this. The segway can be anywhere here at equilibrium at x1 bar. The angle should be necessary like here or like this. Okay, so it means that k pi. So normally I prefer like this, of course, but the other one with the body down was also an operating point. For the second question, I have to linearize the system around an operating point, of course, but I choose the operating point such that the system is at an unstable equilibrium point. So it is an upper point, of course, when the body is at the top. And the linearization, for the linearization, I will consider s equal to 0, but as we can understand, the linearization will not depend on s. Recall that the system is given by this state equation, and the operating point I choose is x bar is equal to, so recall that it corresponds to s bar, theta bar, s dot bar, theta dot bar, and this one for theta bar it is more or less k pi. Since I consider the upper point, I will consider that it is equal to 0. S bar is also taken as 0, and this one also equal to 0 due to this. And also u bar is equal to 0. Okay. So now I will have to find a first order approximation of this function f of x and u near to x bar u bar. So then I will obtain a linear approximation of this function. So I know that cos x2 around x bar is approximately equal to 1. Okay, so there is no first order approximation. After I will have something which is of the order of the norm of x2 x of x square. So it corresponds to a first order approximation. But an approximation of x3 at the first order is approximately around x bar equal to x3. Sine of x2 is approximately equal to x2 and so on. So how can I explain this? Oops, excuse me. If I consider the sign like this, then the first order approximation is like this. So it corresponds to x2. But if I consider the cosine, such as here, the first order approximation is something like this. So there is a 0 for the slope. So it means that this one I can replace by x2. So I can remove the sign. This one, x4, is approximately equal to x4, but x4 square is approximately equal to 0 at the first order. So I can remove this. This one, cos of x2, I can remove it. I can replace by 1. So I remove it. When I remove it, it's equal to 1. This one, I remove the sign only, not the x2. This one, I remove it. This one is approximately equal to 1. This one also. And then I obtain something which is linear with respect to x2 and u x2. So the first order approximation of this one, it's equal approximately around x bar by something like x dot equal to, so here I will have 0, 0, 1, 0, x. So here the 1 is due to the x3 plus something multiplied by u. For the second one, due to the x4, I will have 0, 0, 0, 1. And then after, I will have 0 minus mu 3 mu j due to this divided by, so it's mu1 mu2 minus mu3 square zero zero. And for the last line, also I have a component with respect to x2, so I will have mu1 mu j divided by, again, mu1 mu2 minus mu3 square 0 0. And for the component with respect to u, I will have here mu2 plus mu3. So here 0 0 divided by the same, so mu1 mu2 minus mu3 square. And again here I will have minus mu1 minus mu3 divided by mu1 mu2 minus mu3 square. So it is my first order approximation. This corresponds to the matrix A, and this one to the matrix B. Also, I have my observation function, which is linear, which is like this. x plus 0 times u, and this matrix corresponds to the matrix C, and the 1 tells me that I am able to measure the angle of the wheel only and nothing else. So from this state equation, linear approximation, I will be able to compute the controller. Question number 3. By using the controllability matrix, we have to determine whether the system is controllable, but of course it is not required here. But in practice, it is important to check that the system is also observable, so that we can control it, and we can control it with a state estimator also. Here it is not only asked to check for the controllability. So for this, I need to, for this question, controllability, I take the matrix of controllability matrix, which is given by B, A, B, and so on. So A times B, and power 3B. So B is this vector. So I will have obtained, I stop here because it is n minus 1, and n, the dimension of x, is equal to 4. B is a vector, so it means that in our specific case, we have a square matrix, which depends on this coefficient. So for instance, I will call it this one is, so this one will be B1, this one will be B3, this one B4, and also here I will have A3, 2, and this one is fourth line, so A4, second column, A2. So I know this coefficient. So also in our specific case, I will have the first column which corresponds to B, 0, 0, B3, B4. So I multiply by this, and due to the 1 which are here and the 0 here, I obtain something which is quite simple. B3, B4, 0, 0. Here 0, 0. B4, A3, 2. B4, A4, 2. B4, A3, 2. B4, A4, 2, 0, 0. So this is a controllability matrix, and I have to check that its rank is equal to is a full rank. So this matrix has a rank equal to 4. So for this, since it is square, I have to compute its determinant and to check that the determinant of the matrix M is equal to 0, if or not if. So I prefer, of course, that it is not equal to 0, but I check the condition where I have not the controllability. So the determinant is equal to 0, I compute the determinant, and I have something like B4 times B3 A42 minus B4 A32, and I will try to solve and to check when this can be equal to 0. Of course, B4 is not equal to 0 due to the coefficient, so I don't care about this one, and I will check this. And this is equal to 0. I compute with the values with respect to the mu1, mu2, which also depends on the coefficient of the masses and the inertia and so on. And I will obtain that this is equal to 0 if and only if rho m L square is equal to 0. And this is impossible, since the radius, the mass, and the length are all strictly positive. So in our situation, I, I will I can check that it is. So I can check. So I have checked that the gamma com has a rank equal to 4. Thus, it is controllable. This is for the controllability. Normally, I should check for the observability. And for this, I need to check that the observability matrix, which is given by C, CA, CA square, that this matrix, which is also square, is also full rank. So I will not do it here, but it is the case. So from this, I have the matrices A, B, and C that are given by my linear approximation, and I know that I will be able to compute a regulator for this. Question number 4, simulate the system by using an Euler method. So I will consider the following program, which is in Python. And for this, I will need to use Autolib library, which is given on at this URL. So we can see that I have programmed the state equation. Here I have my function f, x, and u, and here the evolution function, which is programmed here. So I can recognize that x corresponds to a vector x1, x2, x3, x4. So I will, for a better understanding of the program, I will transform this vector, which is in a list, and then to put in the variable s theta, and the derivative of s, the derivative of theta, which corresponds to this variable ds and d theta. I have also the denominator den, which is given here, where mu1, mu2, and so on given here, that are already given here and here. The mass, the length, and so on are known, and they are given here. And dt correspond to the sampling time that I took very small, just for a better understanding of the simulation. So now what I return is the derivative, which are computed here. So we can understand that, for instance, this one, x3, corresponds to ds, and ds corresponds to x3. Okay, so this is my function, my evolution function f. Then I will initialize my figure, take an initial state vector x, and perform the simulation inside this loop. I will use for this an Euler method which approximate like this: t of t plus dt is equal x of t plus dt, the small number given here, multiply by f of xt ut. So u, I took it equal to 0, and at each iteration I will clear the figure to avoid the superposition of all these figures. And then here I will draw the segway. I run my program and I obtain here the segway, which is unstable due to the fact that there is not controller yet. So we can understand that the motion is consistent with intuition. Okay, so when the body falls, then the wheel will react on the right direction. Next question. Now we have to find, we assume that we measure the angle S with an odometer, for instance, and we have to compute a linear controller so that the segway goes to the right position. So I can choose S as I want, and the system will go to this point. So to have, I have to choose some stable poles. Here it is required that I put a -2 here, around -2. So it means that the time of the constant time is something like half a second. So it will react in half a second, which is consistent with the physics of the segway. Then we'll propose a simulation to validate the stability of our controller, and we will check the robustness. Question number 5. We have a segway, a planar version of the segway, which is approximated, so around is unstable equilibrium position, by its linear approximation. So the approximation is given by this, and also I have to add y equal to 1000 times x. So this one, two are equivalent. So here the matrix A, the matrix B, and the matrix C. I enter this matrix says A, B, and C into an algorithm named KLH, and this one will return the matrices IR, BR, CR, and DR, which correspond to the state matrices of the regulator. For this, I will have to insert poles which correspond to the speed I want for the controller. So for me, I want here the pole equal to something like approximately -2, which means that they correspond to a constant time of half a second. So it means that if my segway is like this, it will go approximately to 0, to its required position in half a second. Okay, so the corresponding Python program is given here. Okay, where I can recognize the values for A, here B and C. So here A, B and C. But also I need another one which corresponds to E, which tells me to which state variable I want to assign W. So for instance, when I want, for instance, when W equal to 5, it means that there is a correspondence in the system. And the correspondence for me is that I want my system goes toward the position W equal to 5. To give this the signification of W, I use the matrix A. So since I want that that W corresponds to the distance between 0 and the center of the wheel, I will choose U equal to minus rho. So the minus is due to the fact that when S increases, the distance between 0 and the center of the wheel decreases. So that's why I need a minus. Minus rho, the radius of the wheel, and here is 0, 0, 0. So it means that what I want is that W equal to E times X. So I extract from X the first component and I multiply by minus rho so that it corresponds to the required distance. Then I still have my evolution function and I am not allowed to change it since I only have I cannot change the system. I can only change the values for you, and this is the role of the controller to do this. Here I use the KLH controller, which require A, B, C, and E, and also the poles. The poles have to be taken different. It is due to the algorithm that find me AR, BR that place the poles. This one is also given in the Autolib library. So from this I program the output, y, which is a function of x, and c is the observation function. Here it is my regulator, which computes u, and I will insert the corresponding value for u inside the Euler equation. Here, this corresponds to the fact that, as I have written before, the state equation for the regulator, so xr correspond to x hat, is equal to ar x hat plus br times the input, and the inputs are w and y. It is the input of the controller. So recall that the controller has two inputs which corresponds to the set point and also to what I measure, and the role of the controller is to find the output u. That's why here I have u equal to cr x hat plus dr times the input, and the inputs are w and y. Okay, here it is the controller. And of course, this is a differential equation, and I need to integrate this differential equation using an Euler formula, for instance. And here I draw the segway. So this is consistent with what I have written here. So this corresponds to this, which corresponds to this, and also to this equation and this equation. I go to Python. Here, this is my program. I ask the system to go to the position W equal to 2. I run it, and it goes to the position W equal to 2. So if I want my segway go straight on, for instance, I will write here, I will remove this. And I can write here, for instance, W equal to T. So it means that the desired position will move with time now. I run it, and now I can see that the segway goes right with time. So at time t equal to 5, I am at the position 5. The last question, I want to control the three-dimensional segway, and for this I have to add some state variable. So I keep the same state variable as before, but I have removed s, which has no more signification, uh, since there is no central wheel, but instead we will have two wheels, and the angles of the two wheels, so the left and right, will be called now S1 and S2. So no more S, but now the angles of the two wheels, left and right. And then the position and the heading, so X, Y, and C of the segway, have also to be added in a state variable. So recall that there is a relation between the new state model and the previous one. It is that the state variable S now corresponds to the average, uh, mainly its derivative. So the derivative of S corresponds to the average between the speed of the left wheel and of the right wheel. So before proposing a controller, we have to find the model. So we had a planar model, and the planar model was given by this equation. Okay, but now we have a three-dimensional model, and the three-dimensional model, we have to assume that it is stable thanks to the linear regulator. And if I can represent like this, for the three-dimensional model from the top, I have a point here which corresponds to the center of the segway, and here the segway like this. It is the right wheel and the left wheel, and here it corresponds to the speed of the segway. The angle here will correspond to S1 and here S2. Here it will correspond to X and Y, and the angle here correspond to psi, the heading. And I will take the Shah model, and so I will have the following state equation. X dot is equal to the speed S dot cos psi, and Y dot corresponds to S dot times sine of psi. And now, as written in the exercise, I can control the differential between the two wheels left and right, which correspond to the rotation speed of the segway from the top. So it corresponds to U2. And now I have to control the heading and also the speed, and they are related to S1 and S2 directly. So in the previous model, it's the same here as if I have U1 and U1 here instead of U. So if I do this, since as written in the exercise, S dot corresponds to the average between the speed S1 dot and S2 dot, and from this I can assuming that the wall is stable, I can get a mixture between the two-dimensional, the planar model represented here, but also a two-dimensional model from the top. So it's not exactly a three-dimensional model, but the structure of the Segway makes me possible to decompose the three-dimensional problem into one two-dimensional problem, the planar view, but also the top view, so two-dimensional model. If I do this, I will obtain this model. In this model, S does not exist anymore and has been replaced by S1 and S2. S1 and S2 directly the derivative, so here I have this, the derivative of S1 and S2 are directly related to S dot as explained here. Okay. Here I can control, thanks to U2, I can control the derivative of the heading as explained here. Here this corresponds to this, and this and this correspond to the planar model. Okay, so now I can program this system and propose a controller for this. I will first propose a simulation of this system. So this model correspond, we have this evolution function, the three-dimensional one, which is correspond to this function, Python function. Here I have my loop with a layer integration. So I have taken here pitch equal to 0.1 to make the system unstable. So there is no controller due to the fact that u equal to 0. So of course my Segway will fall down. I will run this program and I obtain indeed that the Segway is falling down. It is a three-dimensional view of the Segway. To control the three-dimensional Segway, I have two inputs, U1 and U2. U1 will control the pitch and will use a linear controller that I have computed before on the planar model. And U2 will be computed using a proportional control. So we can see that in the program I will run, this corresponds to U1, where the matrices CR, DR, and so on, and represented here and here. This one corresponds to U1, the linear KLH controller computed on the planar model. Now, for U2, we'll consider proportional control, which tells me that if I want to go to the direction psi bar, then I will apply something which is corresponds to the error, and something which is proportional to this error, proportional controller. The coefficient I will put in front of this error is 1. So this is why I have here U2. I have again my Euler formula, and I extract here the values just for the drawing. The controller is computed here, and this is the initial position. Now I want so the controller here, U1 KLH, this one corresponds to the state X, and here the heading controller, which is given here. I have also W, which in practice does not correspond to the heading, since I want to always to have a heading almost equal to 0. But for the W correspond, to the pitch. So I always want a pitch angle equal to 0. W corresponds to the heading. This is why here I to the heading and also to the speed. Now to apply the previous controller, I will ask here to have a psi bar. So psi bar, I will ask it to go to 1 radian, which means that if here I have x and y, then I want to go to the direction psi bar, which corresponds to 1 radian. This is what I want for the heading. And also for the speed, for the position, I will ask, which corresponds to W in the previous notation, I will ask to have W equal to T, which means that I want to have an evolution which is which corresponds to the time T. It also corresponds to the fact that I want to go forward with a speed equal to 1 meter per second. So if I run this algorithm in Python, which is given here, I will obtain first a transition phase where the segway goes to the right direction, and then it goes forward with a speed equal to 1 meter per second in a stable way. So I was able to control the heading, but also the speed.